Now let's look at the example problem. This is a LeetCode problem called the longest common sequence. So given two strings s and t, the question asks us to return the length of their longest common subsequence. So a subsequence of a string is a new string taken from this string, but you can skip ones. So that subsequence generally means you can skip things. Substring generally means you cannot skip. It has to be a continuous segment. So I want you to pause the video and work out the answer to this particular input. Okay. So the longest common subsequence, there are two of them. So B would match with this B, and D match with this D, and E match with this E. So that's one of them. Or we can also do ADE. So A match with this A, and D match with this D, and E match with this E. So that's the longest subsequence. Now, how do we compute this? So essentially, we can. So the way I like to think about DP problem is, I assume that all the subproblem is solved. All I need to do is to do the last step. So I can assume that for all prefix of s and all prefix of t, I already solved them. So now I need to figure out what is the longest common sequence of the string for s goes to I and t goes to j. So in general, when you do this, it's almost always a case analysis. So we are looking at this prefix of s and prefix t, and we assume that all shorter prefix combinations are solved. So then we look at the last letter. We look at si and tj. So there are two cases. One of them is they're equal. If they're equal, then these will be there will exist a longest common subsequence that's involving this. So because the longest, you can use it, and any other way of using one of these to match. So if instead of si matching with tj, if I match si with tj minus 1, then I can match si with tj, and I can still get the previous subsequence. So matching this will not hurt us. So it will, whatever longest common subsequence that involving matching one of this can still be obtained. The same length can be obtained by making this last match. And of course, if the longest common subsequence doesn't use si or tj, then that cannot be the longest, because now I add this, it becomes longest. So the recursive relation is LCSIJ is 1 plus LCS I minus 1 j minus 1. Now the other case is when they're not equal. So when they're not equal, then these doesn't match. So then there are two. I need to consider two possibilities. One is the longest will be s goes to I minus 1. Yeah, so that's a previous case. Then the s goes to I match with t go to j minus 1, or s goes to I minus 1 matches t goes to j. So when they're not equal, then the longest common sequence has to be one of these two subcases. So that's how we solve this in the recursive relation. Now to write the code, we will be using a bottom-up table. So these table store the length of the longest common subsequence between the prefix of s and prefix of t. So let me see which string is s in this example. So yeah, s is the shorter one. So here in this table, I have s going vertically and the t going horizontally. And I find that for the problem involving two string, it's a little bit more convenient to code if we have a row and column for empty string. So here, what we are saying is an empty string as S, the longest common substring between empty string as S, and all the substrings of T will all be 0. So, and this column is a matching prefix of S with empty string of T. So we can, once we define this table, we can fill this table row by row or column by column. When we are trying to fill, for example, this cell, so these first row and this first column, they're all 0. This can be initialized. When we try to fill this cell, we will compare the two letters. The first letter with S and with the first letter of T, they're not equal. So therefore, it will be max of this or this, and so that's 0. So we compare the next one, we compare this with this, and they are equal. So then we match them, and then we look at this S I minus 1, J minus 1, this is 0, so that therefore the value is 1. So the next one, B and C are not equal. So therefore, we know the longest common sequence will be the max of this value or this value. So and so on. So for example, here we have D matches with D. So we know the LCS will be this value plus 1, so it becomes this one. And yeah, here is E matches E, and here the last one, E is not equal F, so this value should be the biggest value of this or this, so then it should be 3. So this table also enable us to recover longest common sequence. So in fact, it enables us to recover either a 1 or all of them. So we look at the last cell. So this last cell gives us the length. So then if they are not equal, if these two letters are not equal, then these 3 will come from either here or here. Sometimes come from both. Then that means there will be multiple ways to construct this. If there's only one way, then we know we should look at this cell. So this cell matched with E and E are equal. So because the two letters are equal, then that E will be the part of the longest common sequence, and then we can go to the diagonal, go to these two, and this 2 matches this 2. So we go here, and here this is where we can illustrate their 2 longest common sequence. This value is 1, but both the value to the left and the value to top is also 1. So that means either way would work. So these will give us A, D, E, and if we take this will give us B, D, E. So from this table and the 2 strings, we can recover the actual subsequence. So there are many DP problems involving 2 strings, and for most of such problems, the best way to do it is to have this 2-dimensional table, constructing something for all prefix of one string against all prefix of another string. And a lot of time the recursive relationship takes this form in that Aij will depend on Ai minus 1, J minus 1, Ai J minus 1, and Ai minus J, and of course this Si and Tj, the 2 characters. So and oftentimes I find it's easier to code to have a sort of one extra row, one extra column for empty string. Otherwise, you need the boundary check. So it's not absolutely necessary to have this extra row and extra column, but I like it that way. So this is a template code for solving 2-string DP problems. So let me So there are a list of so the one later slide have a long list of 2-string DP problem in LeetCode, and I think all of them can be solved using this template. So we define this 2D array, m plus 1, n plus 1, initialize 0. Then we need to initialize the 3 initialization, the 0, 0 cell, and the first row and the first column. first row initialized here, and the first column is initialized here inside this loop, and then inside the double loop is update dpij based on these values. So for this particular problem, I think all of the initialization is 0. But for some other problem, we may need to initialize some of this being 1 instead of 0. For example, counting how many ways for things to happen. Then in that case, we actually often initialize this dp00 is 1. So that's it for this problem.